Across the observable universe, nearly every galaxy is racing away from us, as if pushed by an invisible force woven into the fabric of space itself. The farther we look, the faster they flee, some moving so quickly that their light is stretched beyond what our eyes can ever see. This isn't an illusion or a trick of perspective. It's a fundamental truth about reality that scientists spent decades trying to understand. In this video, we explore the mystery behind this universal drift and why it's one of the most profound clues to the universe's origin. Dark energy push. Far out in the quiet reaches between galaxy clusters, where space seems to breathe in slow, ancient rhythms, the influence known as the dark energy push reveals itself as a steady pressure woven into the architecture of the universe. It operates without spectacle, no bursts of radiation, no waves of expanding matter, no dramatic signal to herald its presence. Only a calm, persistent acceleration that reshapes the cosmos over billions of years. Its discovery rests on the shoulders of late 20th century astronomers who studied Type Ia supernovae not for grandeur but for consistency, using their predictable luminosity as a measuring tool. When two research teams, working independently, analyzed these distant stellar explosions, they noticed the light arriving fainter and more stretched than expected. This subtle dimming was the universe's quiet confession. Expansion was not slowing under gravity's familiar pull, but speeding up under the influence of something far stranger. This behavior required a new ingredient, an energy permeating every corner of space, acting equally in all directions. Unlike matter, which clumps and gathers, or radiation, which streams and disperses, dark energy remains perfectly uniform. It does not form structures, nor does it interact with light in any measurable way. All it does is push, extremely gently, on the geometry of space-time itself. Einstein's equations of general relativity accommodate such a presence through the cosmological constant, a term originally introduced to preserve a static universe. When later evidence revealed cosmic expansion, Einstein abandoned the constant, though modern measurements have restored it with renewed legitimacy. This cosmological constant remains the simplest explanation for dark energy, a property inherent to the vacuum, producing a pressure that counteracts gravity on the largest scales. Within galaxies, dark energy is effectively silent. Gravity binds stars into orbits, holds planets in their courses, and anchors entire galactic disks together with unwavering authority. But between galaxies, particularly between clusters separated by hundreds of millions of light years, dark energy's influence grows undeniable. The more space you give it, the more confidently it acts. What it lacks in strength, it compensates for in scale. A gentle outward pressure, applied across vast distances, accumulates like a long, low tide, lifting all boats, subtly but inexorably. Measurements of the cosmic microwave background by missions such as WMAP and Planck show that dark energy accounts for roughly 68% of the universe's total energy budget. This proportion would seem excessive in a novel, yet the universe accepts it without introduction or elaboration. It means that most of what exists is neither matter nor radiation, but a quiet pressure threading through the void. If one were to take the universe at face value, one might assume the galaxies define its behavior, but in truth, it is the empty spaces between them that dictate the cosmic tempo. A small philosophical hum runs beneath this scientific structure. As dark energy continues its gentle insistence, regions of the universe drift irretrievably apart. Galaxies that shine brightly today will, in distant epochs, slip beyond observational reach, not because they accelerate under their own power, but because the space separating them grows faster than light can traverse it. This does not violate relativity. Nothing is moving through space at superluminal speeds. Space itself is stretching, and light simply cannot keep up. Such galaxies will fade from view, not through dimming or collapse, but through expanding distance alone. The horizon of the observable universe becomes less a frontier and more a tide line, steadily retreating outward. Yet dark energy's role is neither malevolent nor dramatic. It establishes the background rhythm against which all other cosmic events unfold. Stars form and die in local bursts of brilliance, galaxies collide and merge in sweeping arcs, and black holes shape their environments with characteristic intensity, but dark energy persists unchanged. A quiet ledger keeper, recording each epoch with calm acceleration, embellishing nothing, interrupting nothing, simply maintaining the universe's long outward breath. Future studies may refine our understanding. Alternative theories exist: scalar fields, modified gravity, or evolving energy densities, but the cosmological constant remains both elegant and sufficient, a demonstration of how the universe often chooses the simplest mechanism to achieve the widest effect. Whether dark energy proves to be fundamental or emergent, constant or variable, its influence continues to expand the universe with unwavering steadiness. Endless expansion. Across the immense sweep of cosmic time, as galaxies drift further into the dark and the fabric of space-time extends with slow persistence, the phenomenon known as endless expansion becomes the defining trajectory of the universe. Unlike earlier expectations that gravity might eventually halt expansion or reverse it into a catastrophic collapse, the evidence now points to a future shaped by the relentless stretching of space. The acceleration discovered in the late 1990 seconds did more than confirm dark energy's presence. It illuminated the universe's long-term direction, revealing that expansion is not merely continuing, but deepening, strengthening, and becoming the central feature of the cosmos. At present, the universe expands at a rate described by the Hubble parameter, a value that has evolved since the Big Bang and will continue to evolve for trillions of years. As dark energy grows in relative dominance, outpacing matter and radiation as the universe ages, this expansion stabilizes toward a near constant rate, giving rise to what cosmologists call a de sitter future. In such a universe, distances do not merely increase, they accelerate exponentially. A galaxy already distant drifts further away at a pace controlled not by its motion, but by the stretching of the space between us and it. Over time, this makes once visible galaxies slip gradually beyond the cosmic horizon, transforming the night sky from a tapestry of millions of distant lights into a quieter, more locally governed scene. Despite this broad cosmic widening, gravitational islands persist. The local group, our Milky Way, Andromeda, and dozens of smaller galaxies remains bound. The upcoming merger between the Milky Way and Andromeda will unfold unaffected by the universe's large-scale acceleration. Gravity dominates on these scales, binding stars and gas into a coherent structure. But beyond this island, the cosmic ocean grows wider, the currents slower, and the distances insurmountable. Over epochs measured in trillions of years, other galaxy clusters will fade entirely from view, leaving isolated structures floating in a vast and silent expanse. Such a future carries implications for cosmology itself. Much of the evidence we rely upon today, the cosmic microwave background, the large-scale distribution of galaxies, the faint red-shifted light of distant supernovae, will eventually become inaccessible. Future observers, situated in this far-off epoch, may find themselves unable to deduce the universe's expansive origins. Without visible galaxies receding into the distance, without background radiation stretched thin across the sky, the early universe's story becomes harder to reconstruct. This era, rich with observational clues, occupies a narrow window in cosmic history. Still, endless expansion remains an observable truth in our time. Measurements from Planck, combined with galaxy surveys, such as the Sloan Digital Sky Survey, show a universe that grows more dominated by dark energy with every passing age. Cosmic structures become less influential across the widest scales. The large cosmic web, once sculpted by gravity's firm hands, begins to freeze in place as expansion outruns the ability of matter to regroup and coalesce. No new galaxies will form once the existing reservoirs of gas are consumed. No new clusters will gather. The era of structure is temporary, a flourish of complexity between two long stretches of cosmic simplicity. While the distant future described by endless expansion might seem austere, it also highlights the richness of this present epoch, where galaxies still communicate through ancient starlight and the universe remains open to inquiry. Expansion has not yet carried the cosmos beyond our ability to learn from it. The patterns remain accessible, the signals still bright enough to decode. This moment, perched between the fiery density of the early universe and the dim quietude of its remote future, offers the ideal vantage point for understanding cosmic history. Following the arc of expansion draws us toward another layer of the universe's structure, where the vast outward motion gives way to the quiet persistence of gravitationally bound systems, the enduring islands that remain intact even as the wider cosmos drifts into widening silence. Cosmic drift, across the vast quiet between galaxies, where distances stretch beyond any familiar scale. The phenomenon known as cosmic drift appears as the gentle separation of structures carried along by the universe's continual expansion. It is not a motion in the traditional sense, no engines firing, no thrust, no wind pushing against cosmic shores, but rather the passive consequence of space itself widening, steadily altering the relationships between galaxies, as though the entire cosmos were exhaling over billions of years. The term captures the subtlety of it. Galaxies do not surge outward under their own power. They simply come to occupy positions that grow ever farther apart because the underlying fabric of space-time is stretching. The idea first came into scientific focus in the early 20th century, when astronomers such as Vesto Slipher measured unexpected redshifts in the spectral lines of distant galaxies. Light that should have appeared at precise wavelengths arrived stretched, shifted toward the red end of the spectrum, as though the galaxies emitting it were moving away. Edwin Hubble later demonstrated that this redshift was not merely incidental but correlated with distant galaxies, twice as far away, exhibited roughly twice the redshift. This relation suggested a universe not fixed and unmoving, but expanding uniformly in all directions. What appeared to be galactic motion was, in fact, the drift produced by an expanding metric. In an intuitive sense, one might picture small beads resting on a rubber sheet. If the sheet is stretched evenly, the beads separate without any bead exerting effort. Cosmic drift is this effect writ across the observable universe. Each region of space expands relative to others, and the structures contained within it follow suit, carried gently outward by the growth of space-time. Gravity resists this at smaller scales. Galaxies remain bound, star systems hold together, planets orbit their stars with quiet regularity, but on scales of tens or hundreds of millions of light-years, gravitational bonds weaken and drift becomes the dominant behavior. The mathematical framework for this expansion lies within general relativity. Einstein's field equations allow space-time to curve and evolve depending on the distribution of matter and energy. Solutions, such as those proposed by Alexander Friedmann in the 1920 seconds, showed that the universe need not remain static. It can grow, shrink, or evolve according to its density and composition. As later measurements revealed, the universe contains a mixture of ordinary matter, dark matter, and dark energy, each contributing differently to its dynamic behavior. Cosmic drift emerges naturally from these equations. When the sum of pressures and densities favors expansion, space-time stretches, increasing the separation between unbound structures. This drift is slow by human standards. A galaxy a million light-years away drifts only a few dozen kilometers farther each second, utterly imperceptible on earthly scales. Yet over cosmic timescales, this gentle pace becomes transformative. A billion years from now, the same galaxy will sit tens of thousands of light-years farther away. Drift is the patient sculptor of the large-scale universe, redrawing distances with a calm persistence that mirrors geological transformations on Earth, though occurring across a canvas far larger. While cosmic drift operates everywhere in the universe, it is not uniform in its effects. In regions rich with matter, gravity competes with expansion. Galaxy clusters resist drift internally, maintaining structure through mutual attraction. Within clusters, galaxies orbit one another, fall inward, collide, and merge. But between these clusters, where matter thins and gravity's influence weakens, drift proceeds with fewer constraints. Over hundreds of millions of years, clusters become more isolated, separated by widening voids that limit gravitational influence across vast distances. From an observational standpoint, cosmic drift has another subtle consequence. It stretches the wavelengths of photons as they travel through expanding space. Even if a galaxy emits light at a precise frequency, the intervening expansion elongates the light's wavelength by the time it reaches us. This redshift provides a record of the amount of expansion that has occurred during the photon's journey. In this way, each distant galaxy becomes a time capsule, its light carrying encoded information about the history of cosmic drift since its emission. Such drift shapes the observable boundary of the universe as well. Because expansion accelerates, driven by dark energy, distant regions recede faster than light can traverse the stretching space between us. Although no physical object exceeds the speed of light relative to its local surroundings, the cumulative effect of expansion places some galaxies permanently beyond reach, not through power or velocity, but through the simple widening of spacetime. Cosmic drift, in this sense, sets the limits of our cosmic horizon, determining what can be seen and what remains forever beyond detection. Viewed at this scale, drift becomes not merely a physical phenomenon, but a subtle philosophical companion to astrophysics. It suggests a universe in motion without insisting on movement, a gradual separation that requires no force, no struggle. Just as cultural landscapes evolve over centuries, while individuals notice little change in their lifetimes, cosmic drift reorganizes the universe with such patience that no civilization could witness more than a fraction of its transformation. Yet the evidence surrounds us in every redshifted photon. Drift's elegance lies in its minimalism. It does not alter the internal dynamics of galaxies, disturb planetary systems, or disrupt the delicate structures of stellar nurseries. Instead, it works in the spaces between, altering relationships gently but irrevocably. In doing so, it creates a universe where structure is both possible and temporary, where connections form under gravity's guidance and drift apart under expansion's quiet influence. This broadening of cosmic distances, steady and unhurried, naturally draws attention toward the next scale of behavior, where the gentle drift transforms into something more pronounced. As distances increase and expansion becomes more apparent, the observational signatures grow sharper, guiding us deeper into the patterns that reveal how galaxies themselves participate in this outward motion, each carrying a trace of the universe's expanding story across immense spans of cosmic time. Galaxies receding high above the plane of the Milky Way, where the starlight thins into a faint silver wash. The behavior described as galaxies receding becomes clear through the quiet evidence carried in the light of distant systems. It refers to the measurable fact that almost all galaxies outside our local group are moving away from us, their velocities revealed through the stretching of their emitted light into longer, redder wavelengths. This recession is not the result of galaxies travelling through space at extraordinary speeds. Instead, it is space itself that expands, lengthening the path between us and them. The galaxies merely trace this expansion, carried outward as if resting upon a current too slow to feel, yet too persistent to resist. The first confirmed measurements of galaxy recession arose in the early 20th century, when Vesto Slipher recorded the Doppler shifts of spiral nebulae. Many of these nebulae exhibited redshifts far larger than could be explained by local motions. His observations, while initially enigmatic, hinted at a broader cosmic pattern. When Edwin Hubble later determined the distances to these nebulae, now recognized as galaxies, he uncovered a linear relationship. The farther a galaxy, the greater its redshift. This finding, formalized in 1929, laid the foundation of modern cosmology. The universe was expanding, and galaxies were receding from one another in a manner consistent with an evolving space-time. This recession is described quantitatively by the Hubble-Lemaitre law, where a galaxy's velocity is directly proportional to its distance. A galaxy twice as distant recedes twice as quickly. This relation emerges naturally from general relativity and is independent of any specific galaxy's internal behavior. A galaxy may rotate, form stars, collide with neighbors, or drift among clusters. Yet all these motions overlay a deeper expansion that carries galaxies away on average. Even the peculiar velocities produced by gravitational interactions cannot overturn the overall trend. Virtually all galaxies outside our gravitationally bound region exhibit positive redshifts. Recession is not motion in the classical sense. No galaxy experiences a wind of space against its surface, nor do stars within it adjust their orbits in response to some outward pull. Instead, the recession manifests as a geometric effect, where the distance between 2 points increases because space-time's metric evolves. This distinction resolves several conceptual difficulties. For example, galaxies can appear to recede faster than the speed of light at sufficiently large distances without violating relativity, because no object is travelling through space superluminally. The space between us and those galaxies is expanding, increasing the total separation at a rate exceeding what light can bridge. As observations have improved, particularly with data from the Sloan Digital Sky Survey and deep field images from the Hubble Space Telescope, the recession of galaxies has become a tool for tracing the universe's expansion history. By comparing the redshifts and distances of galaxies across billions of light years, astronomers reconstruct how expansion has changed over time. These measurements confirmed a surprising reality. The recession is accelerating. Galaxies are not merely drifting outward. The rate at which they drift increases over cosmic time due to dark energy's repulsive influence on space-time. This acceleration alters the future visibility of the cosmos. Galaxies presently observable at extreme distances may, in future epochs, slip beyond the cosmic horizon as expansion outpaces the arrival of their emitted light. Their spectra will stretch into longer wavelengths, eventually beyond the reach of any conceivable detector. Over trillions of years, only the closest gravitationally bound structures will remain visible. The universe becomes increasingly fragmented, not through destruction but through separation. The recession of galaxies also provides essential information about cosmic age. When cosmologists calculate how recession rates have evolved, they infer the approximate time since all galaxies were much closer together, a value now measured with high precision through the cosmic microwave background. Combined with the Hubble-Lemaitre law, these data yield the universe's age of roughly 13.8 billion years. In this way, the quiet retreat of galaxies becomes a clock marking the tempo of cosmic evolution. Though recession offers a grand portrait of expansion, it also highlights a structural grace in the universe's design. Gravity shapes galaxies and clusters into order, while expansion arranges the wider cosmos into a vast web, where filaments of matter stretch between immense voids. The recession of galaxies does not erase this structure, it simply enlarges the canvas upon which it is drawn. Over time, the filaments thin and stretch, yet their architecture remains legible, a testament to the early universe's imprint. The patterns revealed through recession carry us gently to another layer of the cosmic landscape, where expansion interacts with gravitational islands and dark energy's influence becomes increasingly dominant. In this broader view, the shifting balance between attraction and separation ushers us toward the next consideration in this cosmic tour, where the universe's acceleration reshapes both its present form and its distant future. Invisible stretch across the deep stillness between galaxy clusters, where space carries no scent of motion yet quietly alters its own proportions. The phenomenon known as invisible stretch unfolds as the subtle growth of the universe's underlying geometry. It is an expansion with no visible mechanism, no pressure wave, no outward wind, simply the gradual increase in separation between points in space-time occurring everywhere at once. This behavior is central to modern cosmology, arising directly from solutions to Einstein's field equations proposed by Alexander Friedmann in the 1920 seconds. Those mathematical treatments showed that if space-time contains matter and energy distributed in large-scale uniformity, its geometry cannot remain fixed. It must change over time. The invisible stretch is the manifestation of that change, as calm as the turning of a shadow, yet fundamental to the universe's structure. This stretching first revealed itself not through theory, but through the light of distant galaxies. Early observations by Vesto Slipher uncovered that many spiral nebulae exhibited unusual redshifts. Spectral lines shifted toward longer wavelengths. When Edwin Hubble later measured the distances to these nebulae, a clear pattern emerged. The farther the galaxy, the greater its redshift. That relationship indicated that space was stretching and the galaxies were receding not because of local motion, but because the metric they were embedded in was expanding. This subtle stretching of light waves as they travel through the expanding universe provides one of the clearest observational signatures of the invisible stretch. Though this stretching acts on everything, its influence is not felt equally across all scales. Within galaxies, gravity dominates. Stars orbit their centers undisturbed by expansion. Atomic structures remain fixed. Planets continue tracing their paths through gravitational wells. The invisible stretch becomes apparent only across vast distances where gravitational binding is weak. Between galaxy clusters, between filaments of the cosmic web where matter is too sparse to resist, the stretching occurs freely, extending the gulf between structures with steady patience. The mathematics underlying this behavior lies in the scale factor of the Friedmann Lemaitre-Robertson-Walker cosmological model. This scale factor describes how distances evolve over time, with its rate of change determining the universe's expansion speed. Crucially, this stretch affects all wavelengths of light passing through space. Photons emitted at specific frequencies arrive elongated, their colors shifted toward red or infrared. The amount of stretch a photon experiences provides a record of how much the universe expanded during its journey. Observatories such as the Sloan Digital Sky Survey and instruments aboard the Hubble Space Telescope have mapped these redshifts across millions of galaxies, tracing the invisible stretch across billions of years of cosmic history. Yet stretching space does more than alter distances and wavelengths. It changes the meaning of motion itself. In ordinary experience, distance increases because objects move. But in cosmology, objects can remain at rest relative to local space-time, and still the distance between them can increase. This distinction is subtle but essential. Two galaxies can be at rest within their own local coordinates and still find themselves receding from each other simply because the metric connecting them has grown. From this perspective, recession velocity is not a literal speed, but a geometric consequence, a rate at which space is stretching. Over the past 2 decades, observations have shown that this stretching is not slowing down under gravity's influence, but accelerating. Dark energy, an enigmatic component comprising roughly 68% of the universe, exerts a pressure that causes the scale factor to grow more rapidly over time. This acceleration means that the invisible stretch becomes more pronounced as the universe ages. Distant galaxies drift further and faster. Light grows more deeply red-shifted. The cosmic web expands into a wider and more sparsely connected structure. The philosophical tone, often associated with this behavior, arises from its quiet inevitability. Expansion does not require activation. It does not switch on or off. It continues with steady indifference, altering the landscape of the universe while preserving local structures. Galaxy clusters remain bound, stars continue to evolve, planets orbit their suns, as they always have. Yet across the cosmos, a slow widening proceeds, drawing galaxies away from one another and gradually redefining the limits of what can be observed. This widening also shapes the universe's future visibility. Some regions have already drifted beyond the cosmic horizon, their light incapable of bridging the ever-expanding space between us. Their disappearance is not dramatic. It occurs as wavelengths stretch into bands no instrument can detect. Over trillions of years, more galaxies will follow, as the invisible stretch carries them beyond reach. What remains observable will be the structures bound by gravity. Local groups, clusters, and superclusters that form islands in an increasingly distant sea. What gives the invisible stretch its significance is not its speed, but its persistence. Over billions of years, a centimetre of expansion becomes a light year becomes a million becomes a billion. The universe we see today, rich with galaxies, filaments, and structures, is shaped by the accumulation of this steady, stretching from the earliest epoch after the Big Bang to the present age. It is a phenomenon that works quietly, yet transforms everything. Still, within this expanding stage, the forms of matter continue to shape their surroundings, constructing gravitational environments that anchor stars, planets, and clusters against the broader tide. As those structures interact with expansion, the next concept emerges naturally from their interplay, guiding us toward the wider behavior that defines how space continues to grow around and between the galaxies themselves. Growing space. High above the swirling disks of galaxies, where their light fades into the faintest strands of intergalactic glow, the concept known as growing space reveals itself as the continuous enlargement of the universe's fabric. It refers not simply to motion, nor to the spreading of matter outward, but to the literal increase in the amount of space between unbound structures. This idea sits at the heart of modern cosmology, expressed through the dynamic solutions of general relativity that permit space-time to evolve according to its energy content. Growing space is the ongoing result of those solutions. A universe in which distances expand, horizons shift, and the scale of cosmic structure changes with time. This growth is described mathematically through the cosmological scale factor, a quantity that tracks how distances evolve as the universe expands. Observations from the cosmic microwave background, particularly those from the Planck satellite, show that the universe began in an extremely hot, dense state and has been expanding for approximately 13.8 billion years. As the scale factor increased, matter thinned out, temperatures dropped, and structures such as stars and galaxies began to form. Yet through all of this, the growth of space persisted, shaping the conditions under which cosmic evolution unfolded. Growing space is not uniform in its effects. Gravity competes with expansion on small scales, binding stars into galaxies and galaxies into clusters. Within these domains, expansion is essentially absent. Gravitational attraction dominates completely. But beyond these bounds, where matter is sparse and gravitational influences weaken, space grows freely. Voids between clusters stretch wider, filaments elongate, and superclusters drift apart. This behavior produces the large-scale structure of the universe, a cosmic web of matter suspended within an ever-growing background. Evidence for this growth is clearest when examining the redshift of distant galaxies. Light emitted billions of years ago carries the imprint of expansion, its wavelengths stretched as space grew during the photon's journey. This redshift provides a timeline of how the universe has expanded, allowing astronomers to reconstruct the scale factor's history. Surveys such as the Dark Energy Survey and the Baryon Oscillation Spectroscopic Survey have mapped these patterns across enormous volumes, showing how the growth of space has shaped the distribution of galaxies and the size of cosmic voids. Yet growing space does more than alter distances. It determines the universe's future. As dark energy has become the dominant component of cosmic energy density, expansion has accelerated, causing the scale factor to grow at an increasing rate. Galaxies currently visible at the edge of the observable universe will one day slip beyond detection, their light unable to traverse the rapidly expanding space between us. Structures not gravitationally bound will recede indefinitely, becoming isolated islands within an expanse that grows colder and darker over trillions of years. This leads to a subtle but profound shift in perspective. The universe is not expanding into anything. There is no external space waiting to be filled. Growing space means that the metric itself, the measure of distance, changes with time. New space does not appear at the edges, but arises everywhere simultaneously. Two galaxies 1 billion light-years apart do not drift towards some external void. They remain where they are in their local frames, yet the distance between them increases naturally as space-time evolves. Such behavior raises interesting contrasts with familiar motion. In everyday life, movement is defined relative to fixed space. On cosmic scales, however, space itself is the evolving entity. Galaxies do not need to move for distances to change. Planets do not need to accelerate for orbital periods to remain stable. Growing space writes its changes into the background itself, setting the conditions under which all other motions occur. This growth even affects fundamental cosmological measurements. The Hubble parameter, often interpreted as a speed, is in fact a rate of expansion of space per unit distance. Its value has evolved significantly through cosmic history, decreasing from extremely high values in the early universe to more moderate ones today. Though local regions remain unaffected, the large-scale structure responds profoundly to this changing rate, determining how clusters form, evolve, and eventually drift beyond each other's influence. Growing space also plays a crucial role in the cooling of the universe. As space expands, the wavelengths of photons increase, reducing their energy. This effect has stretched the cosmic microwave background from the blistering radiation of the early universe into the cold microwave glow we observe today. The temperature of this background continues to fall, mirroring the universe's expansion as space grows. Amid these immense changes, local gravitational systems maintain their coherence, offering the universe a tapestry of structures that endure against expansion's wider influence. These persistent forms provide a natural route toward the next layer of cosmic behavior, where the relationship between structure and the expanding background becomes a guiding thread through the evolving landscape of the universe. Balloon analogy. Along the gentle curve of an inflating surface, where tiny markings drift apart without taking a single step, the balloon analogy offers one of the clearest ways to understand how cosmic expansion works. It is a comparison used throughout modern cosmology, not because it simplifies the universe into something childish, but because it captures an essential truth. When space expands, galaxies recede from one another, even if none of them are moving through space in the conventional sense. In the analogy, each galaxy is represented by a small dot drawn on the skin of a balloon. As the balloon inflates, the skin stretches and the dots drift farther apart. Their separation grows not because the dots travel outward, but because the surface beneath them expands everywhere at once. This analogy, though modest, encodes a key insight from general relativity. The universe's geometry can evolve over time, altering distances without requiring objects to move across a static background. When Alexander Friedmann proposed dynamic solutions to Einstein's equations in the 1920 seconds, he showed that an expanding universe is a natural outcome when matter and energy are distributed uniformly on large scales. The balloon becomes a two-dimensional stand-in for the three-dimensional space we inhabit, and its inflation mirrors the changing scale factor that defines cosmic expansion. The analogy is limited. Expansion happens throughout the universe, not from a central point, and our universe has no surrounding air, but the core idea holds. Distances increase because space stretches. One of the strengths of the balloon analogy is that it reinforces a crucial cosmological truth. There is no center of expansion. Each dot on the balloon observes all other dots drifting away. In the same way, every galaxy in the universe perceives neighboring galaxies receding from it. This effect arises because expansion is intrinsic to space-time itself. There is no privileged position, no cosmic origin point expanding outward. Instead, the expansion is uniform, occurring everywhere with equal fidelity. A resident on any galaxy, whether in the Milky Way or some distant spiral, would measure similar recession patterns. The analogy also clarifies why more distant galaxies appear to move away faster. As the balloon stretches, the dots spaced farther apart experience a greater increase in separation for each increment of expansion. This parallels the observational relationship discovered by Edwin Hubble in 1929. Recession velocity grows proportionally with distance. This connection forms the basis of the Hubble-Lemaitre law, a foundational piece of modern cosmology. In the balloon metaphor, two neighboring dots might drift apart slowly, while dots placed on opposite sides of the balloon drift apart more rapidly, simply because more expanding surface lies between them. Although the balloon analogy is useful, it also highlights its own limitations, which in turn illuminate the behavior of the real universe. For instance, the analogy suggests that galaxies expand along with space, but actual galaxies remain gravitationally bound. Their internal structures, the distances between stars and planetary systems, do not stretch as the universe expands. Gravity resists expansion on small scales, maintaining the coherence of galaxies and clusters. In the balloon metaphor, this would be akin to drawing tiny circular rings around the dots that do not stretch even as the balloon inflates. While the surface grows, the internal structure of each ring remains fixed. Another subtlety lies in the balloon's boundary. Our universe does not expand into a pre-existing external environment. The balloon appears to grow into the surrounding air, but cosmic expansion happens without reference to an outside medium. New space does not emerge into a container. The metric that defines space-time simply changes. The balloon's inflation is only an analogy for relative distances, not a literal representation of what space is doing. Despite these limits, the balloon analogy remains indispensable when teaching the concept of expansion, particularly because it encapsulates the idea of cosmological redshift. As the balloon stretches, the distance between successive peaks of a wave drawn upon it grows. In the universe, light emitted from distant galaxies experiences this same effect. Its wavelength becomes stretched as it travels through expanding space, shifting its color toward the red. This directly connects the analogy to observable phenomena that underpin modern cosmology. There is also a quiet philosophical undercurrent to this comparison. It reveals the universe to be more dynamic than it first appears, not a static stage upon which events occur, but a participatory structure that evolves with time. Expansion becomes a gentle rhythm, altering the fabric of reality without disturbing the structures anchored within it. The balloon analogy makes that enormous concept accessible, allowing one to feel the serenity of cosmic expansion rather than seeing it solely through mathematical abstraction. In this sense, the analogy becomes a bridge, linking intuitive understanding with the more technical frameworks of cosmology. It opens a path into deeper ideas, guiding us toward the observational signatures left behind by expansion. Those signatures, revealed through the stretching of light across immense distances, form the next step in understanding how the universe records its own growth through the quiet drift of spectral lines, redshift glow. Across the great distances that separate galaxies, where light travels for billions of years through the widening fabric of space-time, the phenomenon known as redshift glow reveals the universe's long record of expansion. It is the subtle elongation of a photon's wavelength as it journeys through growing space, a stretching that shifts its color toward the red end of the spectrum. This effect is not caused by motion alone, though motion can contribute. It is principally a response to expansion itself. As the universe grows, every wavelength of light traveling through it grows proportionally. What begins as ultraviolet may arrive as visible light, and what begins as visible may fade into infrared through nothing more than the universe's quiet stretching. This behavior first became evident when astronomers like Vesto Slipher observed unexpected redshifts in the spectral lines of distant nebulae. These spectral signatures, normally fixed at precise wavelengths determined by atomic transitions, appeared shifted. It was Edwin Hubble who linked these shifts to distance, demonstrating that the farther a galaxy lies, the greater the redshift in its emitted light. This linear relation now a cornerstone of observational cosmology, confirmed that redshift is not simply a Doppler effect from galaxies fleeing through space, but an imprint of expanding geometry. Redshift glow provides a way to measure that expansion. Its magnitude, expressed through the parameter z, tells us how much the universe has stretched since the light was emitted. A redshift of 1 means the universe is now twice its previous size. A redshift of 6 means it is 7 times larger. These values act as markers along cosmic history, allowing astronomers to determine when events occurred, how structures formed, and how the universe evolved from its hot, dense origins to its present state. The stretching of light also reveals the acceleration of expansion discovered in the late 1990 seconds. Observations of distant type Ia supernovae showed that their redshifts did not align with a universe slowing under gravity, but with one accelerating under the influence of dark energy. This discovery reshaped modern cosmology. It implied that the rate of redshift increase grows over time, meaning distant galaxies recede faster correlatively with expansion's accelerating pace. Redshift glow also affects the cosmic microwave background, the faint afterglow of the Big Bang. Originally blisteringly hot, this radiation has been stretched by expansion until it now resides in the microwave portion of the spectrum at a temperature of 2.725 Kelvin. Its pattern of slight temperature variations carries within it a record of early cosmic structure, sound waves in the primordial plasma, and the density fluctuations that would one day form galaxies. Without the stretching of its wavelengths, this glow would still blaze across the sky in visible or ultraviolet light, utterly transforming our night sky. From a scientific standpoint, redshift is both a measurement and a narrative device. It tells the story of how far light has travelled, how much the universe has grown during that journey, and how structures have evolved through time. The light of a distant galaxy does not simply illuminate that galaxy. It illuminates the history of the cosmos between its emission and arrival. Redshift also affects how we interpret distances. In a static universe, calculating distance would be straightforward, but in an expanding universe, distances change even while light is en route. This makes cosmological distance measurements uniquely complex. Several definitions, co-moving distance, luminosity distance, angular diameter distance, emerge as tools to interpret redshifted light accurately. Redshift glow is the observational anchor from which all these calculations begin. Beyond its technical importance, redshift imparts a quiet, poetic truth. Light is shaped not only by its source, but by the space it crosses. A photon carries the memory of its birthplace, but also the signature of every kilometre of expanding universe it experiences. It becomes a traveller, altered by the journey itself. As the universe continues to expand, the wavelengths of distant light will stretch further still, eventually slipping beyond the reach of future observers. Galaxies visible today at high redshift may one day fade entirely as their light is carried into wavelengths no instrument can detect. Redshift glow is thus a temporary gift of the cosmic era we inhabit, a window into the deep past, afforded by a universe still young enough to reveal its history through the light that reaches us. The stretching of light, calm and relentless, guides us toward an even broader understanding of how cosmic structures respond to expansion. As the glow records distance and time, another layer of cosmic behavior emerges in the spaces between galaxies, shaping the patterns that define the universe on its grandest scales. Distant signals. Out in the far reaches of the observable universe, where the faintest traces of light drift across billions of years to reach us, the phenomenon described as distant signals emerges as the universe's quiet testimony of its own history. These are not merely beams of illumination from remote stars and galaxies. They are fragments of time, stretched and softened by the expanding cosmos, carrying within them the imprint of conditions that existed long before Earth formed. Every photon that arrives from such distances has endured a journey shaped by the growth of space itself, accumulating changes to its wavelength, its direction, and even its encoded structure as it travels through an ever-widening universe. Much of what we know about cosmic evolution derives from these distant messengers. When astronomers first measured the redshifts of galaxies, they realized that the light they observed had been stretched, elongated by the expansion of space during its journey. This process transforms distant signals into living records of cosmological behavior, marking each photon with a history of the growth it experienced while crossing the cosmos. Instruments such as the Sloan Digital Sky Survey and the Hubble Space Telescope have mapped millions of these signals, revealing a universe structured by filaments, voids, and clusters of matter that formed under the influence of gravity and expansion intertwined. Some signals reach us from unimaginable depths of time, including those from galaxies more than 13 billion light-years away. Their light began travelling when the universe was only a few 100 million years old, a period known as the cosmic dawn, when the first stars ignited and ionized the hydrogen around them. Observatories such as JWST now capture these early signals with unprecedented clarity, allowing us to peer back into epochs once thought permanently hidden. What we observe in these ancient galaxies is not merely their light, but their state of formation, small, compact, and bursting with star formation under conditions entirely different from later cosmic eras. Other signals come not from galaxies, but from the early universe itself. The cosmic microwave background, the afterglow of the Big Bang, fills the sky with faint radiation corresponding to a temperature of just 2.725 Kelvin. Its uniformity and slight fluctuations encode information about primordial density differences, forming a cosmic map of the seeds from which all galaxies eventually grew. This background radiation is the oldest signal we can observe directly, dating back roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. Missions such as COBE, WMAP, and Planck have measured this glow with exquisite precision, revealing a wealth of cosmological parameters: the universe's age, its composition, and its geometry. Not all distant signals arrive as light. Some come as neutrinos, ghost-like particles that pass through stars, planets, and entire galaxies with scarcely any interaction. The cosmic neutrino background, though currently undetectable, is predicted to exist as a remnant of the early universe, carrying information from times earlier than even the microwave background. Gravitational waves, too, serve as cosmic signals. First detected in 2015 by LIGO, these ripples in space-time trace the merging of black holes and neutron stars. Future instruments such as LISA will detect gravitational waves from even more ancient events, adding another layer to the distant signals that reveal the universe's tumultuous past. Across these varied forms, distant signals share a defining characteristic: they weaken and stretch as they travel. Every photon loses energy as its wavelength expands with the universe, shifting from visible light into infrared and beyond. Every gravitational wave lengthens as it propagates, lowering its frequency. Even neutrinos cool with expansion, their energies gradually diminishing. These changes are not degradations, but natural consequences of the universe's evolving geometry. They are what allow us to interpret the history encoded in each distant messenger. The philosophical resonance of distant signals lies in the interplay of time and distance. The farther we look, the older the signals become, until viewing deep space becomes indistinguishable from viewing deep time. A galaxy observed at a redshift of 10 appears not as it is now, but as it existed more than 13 billion years ago. When we observe the cosmic microwave background, we are seeing the universe in its infancy. Astronomers often remark that telescopes act not as spatial instruments, but as time machines, though in truth they reveal the simple fact that light cannot outpace time, it only travels through it. Distant signals also impose limits. Beyond a certain redshift, the expansion of the universe becomes so rapid that light emitted today will never reach us. These unreachable regions lie beyond the cosmological event horizon, their signals lost to the accelerating expansion driven by dark energy. Thus, there exist galaxies whose light we will never see, whose histories will never intersect with ours, creating a boundary between the observable cosmos and the larger universe beyond. Still, the signals we do receive tell a remarkably coherent story, one that unfolds across wavelengths and epochs. They chart the growth of structure, the cooling of matter, the rise of galaxies, and the fading of early light. They show us a universe both ancient and evolving, bound together by physical laws that operate uniformly across billions of light years. Signals continue to arrive, carrying their delicate hieroglyphics of time and expansion. They guide us toward the next layer of cosmic understanding, toward the moment when the pattern in their redshifts revealed something extraordinary about the universe's behavior, leading to one of the most significant scientific discoveries of the 20th century, Hubble's discovery. In the calm, pristine skies above Mount Wilson in the 1920 seconds, where the night appeared stable and unchanging, Hubble's discovery quietly rewrote humanity's understanding of the universe. Working with the 100-inch Hooker telescope, the most powerful instrument of its time, Edwin Hubble measured the distances to faint, fuzzy objects then known as spiral nebulae. Using Cepheid variable stars, whose predictable brightness patterns allow precise distance calculations, he showed that these nebulae were not clouds within the Milky Way, but entire galaxies beyond it. This alone expanded the scale of the universe dramatically, but it was his next observation that transformed cosmology forever. By comparing these distances with earlier measurements of their redshifts, many of which came from the meticulous spectral work of Vesto Slipher, Hubble discovered a linear relationship. The farther a galaxy, the faster it appeared to be receding. This recession was not random nor subtle. It followed a clear, steady trend. Doubling the distance, doubled the velocity. Tripling the distance, tripled it. This correlation became known as the Hubble-Lemaitre law, and it implied for the first time that the universe itself was expanding. Its implications were profound. No longer could the universe be considered static, timeless, or unchanging. The neat, stable cosmos envisioned by earlier astronomers gave way to one in continuous motion, stretching as though carried by a hidden mechanism. Georges Lemaitre, a Belgian physicist and priest, had already proposed a theoretical model based on Einstein's equations predicting this very behavior, but it was Hubble's observations that confirmed it empirically. The universe was not fixed. It had a history, a beginning, and a trajectory. Hubble's discovery rests on the observed redshift in galaxy light. When light from distant galaxies arrives, stretched into redder wavelengths, it indicates that those galaxies have receded since emitting that light. While Doppler motion can produce similar shifts, the universal pattern Hubble uncovered pointed toward a different explanation. Space itself was expanding. Galaxies were not flying apart through space. They were being carried along as the metric expanded. This insight laid the groundwork for the Big Bang theory, which postulates that the universe began in a hot, dense state and has grown ever since. Refinements to Hubble's measurement of the expansion rate, known as the Hubble constant, have continued for nearly a century. Modern observations from the Hubble Space Telescope, the Planck satellite, and other surveys offer extraordinarily precise measurements, though a tension remains between values derived from local observations and those inferred from the early universe. This Hubble tension is one of the great current puzzles in cosmology, hinting that our understanding of expansion may contain deeper layers yet to be uncovered. What remains indisputable is the foundational truth Hubble uncovered. Every distant galaxy tells the same story. Their light shifts in a way that reveals the universe's continual growth. Their positions show the geometry of an expanding cosmos. Their recession provides a timescale for the age of the universe, roughly 13.8 billion years, as now confirmed through multiple independent observations. Hubble's discovery also transformed how astronomers interpret the darkness between galaxies. Where once emptiness was considered mere absence, it is now understood as the stage on which expansion unfolds. The voids between cosmic structures grow wider with time, shaping the large-scale distribution of matter into a vast web of filaments and clusters. Expansion influences not only how the universe looks today, but how it will evolve in the distant future, sharpening the contrast between gravitationally bound regions and those drifting irretrievably outward. There is a quiet elegance to the way this discovery reshaped the intellectual landscape. A simple plot distance on one axis, redshift on the other, revealed a universe dynamic in its very foundation. It showed that the cosmos is not a static backdrop, but a living geometry, changing with time and carrying galaxies along its widening structure. And from this widening of the universe, a broader pattern emerges, one in which light, distance, and expansion interlace to create the grand architecture of the cosmos, guiding us, universal expansion, across the vast architecture of the cosmos, where galaxies drift like lanterns suspended in a dark and widening sea. The phenomenon known as universal expansion reveals itself as the steady increase in the distances between unbound structures throughout the universe. It is the overarching behavior first recognized in the 20th century, yet present since the earliest moments after the Big Bang, encoded into the geometry of space-time itself. Universal expansion is not motion in the classical sense. Nothing rushes outward from a central point. Instead, it is the fabric of space that grows, a gentle widening that carries galaxies with it as naturally as a rising tide lifts boats without them ever rowing away. This idea began to take shape when Vesto Slipher recorded unusual redshifts in the light of spiral nebulae. These spectral lines, normally fixed at precise wavelengths defined by atomic physics, appeared shifted toward the red end of the spectrum, stretched in a manner suggesting recession. Slipher's work alone did not reveal the structure of the cosmos, but it laid the groundwork. When Edwin Hubble later measured the distances to these nebulae using Cepheid variable stars, he combined the two datasets and uncovered a profound relation. The farther a galaxy, the faster it appeared to move away. This linear correlation, distance on one axis, recession velocity on the other, became the Hubble-Lemaitre law, the first observational confirmation that the universe was expanding. The mathematics behind this behavior lies in the Friedmann equations, derived from Einstein's general relativity. When these equations are applied to a universe that is homogeneous and isotropic on large scales, they dictate that the cosmic scale factor, the measure of how distances evolve, must change with time. Depending on the universe's density and energy content, it may expand, contract, accelerate, or decelerate. Observations reveal that it has been expanding for roughly 13.8 billion years, beginning with rapid inflation, followed by slower growth governed by matter, and now accelerating due to dark energy. Universal expansion does not influence everything equally. Within galaxies, gravity remains the dominant sculptor. Stars orbit their centers without interference from expansion. Planetary systems behave as though the universe outside them were perfectly static. Even galaxy clusters, groups of thousands of galaxies bound by mutual gravitational attraction, remain unbroken despite the cosmic stretching underway just beyond their edges. Expansion becomes noticeable only on scales where gravity's reach weakens, tens, hundreds, and thousands of millions of light-years. It is here, between clusters, where the fabric of space-time stretches freely and steadily. The expansion of space also stretches light, traveling across cosmological distances. A photon emitted as blue light may arrive as red or infrared, depending on how much the universe expanded during its journey. This cosmological redshift is one of the clearest signatures of universal expansion, allowing astronomers to reconstruct the universe's history from the faint glow of distant galaxies. Instruments such as the Hubble Space Telescope, JWST, and surveys like SDSS have mapped millions of these redshifts, revealing how galaxies populate the cosmic landscape and how expansion shapes their distribution. In the late 1992, Type Ia supernova observations added a new chapter to this story. These supernovae serve as highly reliable standard candles, objects of known intrinsic luminosity. By comparing their true brightness to their observed brightness, astronomers can calculate distances with remarkable precision. When these distances were compared with redshift values, the result defied expectation. The expansion was accelerating. This acceleration hinted at the presence of dark energy, a mysterious component of the universe's energy budget that exerts a repulsive gravitational effect. Today, dark energy accounts for roughly 68% of the universe, making it the dominant influence on its large-scale behavior. Universal expansion also introduces the concept of a cosmic event horizon. Some galaxies are so distant that the space between us and them grows faster than light can traverse it. Though nothing locally exceeds the speed of light, expansion ensures that the separation increases too quickly for photons to ever complete their journey. These galaxies will remain permanently unobservable. As acceleration continues, more will cross this horizon, leaving future observers with a sky increasingly limited to the gravitationally bound structures nearby. Despite its grandeur, universal expansion carries a quiet grace. It does not tear structures apart or impose chaos. It provides the stage on which cosmic history unfolds. Without expansion, the early universe could not have cooled sufficiently to form atoms, stars, or galaxies. Without continued expansion, structures would collapse under gravity's pull. Expansion is the balancing act that allows complexity to arise against a backdrop of ever-increasing scale. In the present era, the universe is richly structured. Filaments of galaxies stretch across billions of light-years. Clusters anchor the nodes of these filaments, and luminous arcs trace the pathways of dark matter's influence. Universal expansion enlarges this structure without erasing it, letting it grow more intricate even as the distances widen. As this widening continues, the universe's large-scale architecture reveals another truth. The matter within it is not scattered randomly, but arranged into a delicate, interconnected lattice formed by gravity acting over billions of years. It is through this gradual weaving that the next great cosmic feature emerges, the immense, branching structure known as the cosmic web. Cosmic web, Threaded across the universe like an immense lattice of glowing filaments, the cosmic web stands as the grandest structure ever observed, sculpted by gravity, dark matter, and the relentless expansion of space. It forms a network that spans billions of light years, connecting galaxies and clusters into elongated strands, leaving behind wide, quiet voids between them. This web-like architecture arises not from random scattering, but from the growth of tiny density fluctuations that existed in the early universe, imprinted upon the cosmic microwave background as faint temperature variations. The first hints of large-scale structure appeared during early redshift surveys, but it was not until the CFA redshift survey in the 1,980 seconds that the cosmic web began to take shape in scientific imagery. When astronomers plotted the locations of galaxies in 3 dimensions, they discovered that galaxies gathered not in uniform distributions, but along sheets and filaments, with enormous voids between them. These early maps captured only a small portion of the universe, yet the pattern was unmistakable. Later surveys, such as the Sloan Digital Sky Survey, SDSS, expanded this view dramatically, revealing a cosmos woven into a vast, interconnected network. At the heart of the cosmic web lies dark matter, the invisible material that makes up most of the universe's mass. Dark matter does not emit or absorb light, but it exerts gravity, and that gravity guides the formation of structure. In the early universe, regions slightly denser than average began to draw in more matter, while sparser regions emptied further. Over time, these density variations evolved into dark matter halos, gravitational wells into which gas flowed, eventually forming galaxies. The halos connected along lines of gravitational influence, naturally producing the filaments and clusters we now observe. Numerical simulations played a crucial role in uncovering the cosmic web's nature. The Millennium Simulation, one of the most famous, modelled the evolution of billions of particles of dark matter over cosmic time. The resulting structures, filaments, nodes, and voids matched observational data with remarkable precision. Such simulations confirmed that dark matter is essential for constructing the universe as we see it. Without it, the web would form too slowly or not at all. Filaments of the cosmic web can stretch hundreds of millions of light years. Each filament contains galaxies, intergalactic gas, and vast reservoirs of dark matter. Galaxies rarely form in isolation. Instead, they trace these filaments, migrating slowly along them over billions of years. Where filaments intersect, galaxy clusters emerge. These clusters, some containing thousands of galaxies, represent the densest and most massive gravitationally bound structures in the universe. Voids, by contrast, are enormous regions where matter is scarce. These empty expanses can span tens of millions of light years, containing only a handful of galaxies scattered throughout. Despite their emptiness, voids play an essential role in the evolution of the web. As matter continues to flow from voids into filaments and clusters, the contrast between regions grows sharper, reinforcing the web's overall architecture. Observationally, the cosmic web reveals itself through multiple techniques. Galaxy surveys show the distribution of galaxies along filaments. Weak gravitational lensing maps trace dark matter by measuring how it distorts the shapes of more distant galaxies. The Lyman alpha forest patterns of absorption, lines in the spectra of distant quasars, provides a map of intergalactic hydrogen that traces filamentary gas. Even the cosmic microwave background carries subtle imprints of the web's gravitational influence through phenomena like the integrated Sachs-Wolf effect. The cosmic web shapes the lives of galaxies. Those embedded within dense filaments experience frequent mergers and interactions, accelerating their evolution. Others, located near voids, evolve more slowly, forming stars at gentler rates. The environment of a galaxy, its position within the web, strongly influences its morphology, star formation history, and the activity of its central black hole. Universal expansion and the cosmic web interact continuously. Expansion stretches large-scale distances, causing clusters and filaments to drift apart, even as gravity strengthens local structures. As dark energy becomes more dominant, the web will gradually thin, filaments will fade, voids will grow, and distant clusters will drift beyond the cosmic horizon. In future epochs, only the densest, most gravitationally bound regions will remain visible, their surroundings swallowed by expansion. Yet, in this present cosmic moment, the web is vividly alive, a monumental structure that reveals how matter has arranged itself over billions of years. The filaments, voids, and clusters form a coherent and elegant pattern, shaped by gravity but expanded by the universe at large. And flowing outward from these patterns, another theme emerges: how local gravitational structures endure within an expanding universe, resisting the widening fabric around them and shaping the landscapes where stars, planets, and life itself may one day arise. Gravity's hold. Across the widening fabric of the universe, where galaxies drift steadily apart under the influence of expansion, there remain pockets of resilience regions where the quiet insistence of gravity prevails, forming what we describe as gravity's hold. It is the counterweight to cosmic widening, the binding force that gathers matter into stars, galaxies, clusters, and smaller gravitational families. In an expanding universe, gravity carves out sanctuaries of structure, places where expansion's reach is simply too weak to pry matter apart. These gravitational islands do not resist expansion through forceful opposition. They endure because, within their boundaries, mass curves space-time strongly enough to maintain coherence. This principle reveals itself first in the familiar architecture of galaxies. For all the universe's expansion, a spiral galaxy like the Milky Way remains stable because the mass contained within it generates a gravitational well deep enough to hold its stars in orbit. Expansion exerts no influence at these scales. The gravitational binding energy far exceeds any separating effect space might attempt. Even on the scale of galaxy clusters, where thousands of galaxies share a common gravitational envelope, the cluster remains intact, drifting through the cosmic web like a single organism adrift in a widening sea. The mathematical description of gravity's hold emerges from general relativity and Newtonian gravity working in tandem. Expansion affects the universe at large, but gravitationally bound systems form stable orbits that expansion cannot disrupt. For two objects to remain bound, their mutual gravitational attraction must exceed the rate at which the space between them expands. This relationship creates a natural boundary, a region where gravity overpowers expansion. Astronomers call this the turnaround radius, the distance at which material no longer falls inward toward a massive object, but instead becomes carried outward by cosmic expansion. Every galaxy cluster, every massive halo, has such a boundary, defining the edge of gravity's local influence. Consider galaxy groups such as our local group. The Milky Way and Andromeda are currently separated by about 2.5 million light-years. But their mutual gravitational attraction far exceeds any expansive influence between them. Their orbits are drawing them together. In roughly 4 billion years, their halos will merge, and their stars will swirl together in a new galactic form. Meanwhile, galaxies beyond the local group drift steadily away, crossing thresholds where gravity can no longer counteract expansion. This simple contrast shows how gravity's hold governs cosmic relationships with gentle but unyielding logic. Beyond galaxies and clusters lies the deeper foundation of gravitational structure: dark matter halos. These invisible halos provide the scaffolding for most bound systems. Dark matter's gravitational influence is far stronger than the mass of visible stars, ensuring that galaxies remain cohesive. The rotation curves of spiral galaxies, where stars far from the center move faster than expected, offer one of the strongest pieces of evidence for dark matter's presence. Without dark matter strengthening gravity's hold, galaxies would not remain intact. Their stars would drift away into the intergalactic void. Gravity's influence extends down to smaller scales as well. Planetary systems remain secure because the Sun's mass dominates the surrounding spacetime. Expansion is immeasurably weak at the scale of solar systems. It exerts no meaningful effect on planetary motion. Even within atoms, where forces are far stronger than gravity, the notion of expansion becomes irrelevant. Gravity's hold is thus not a single phenomenon, but a continuum of binding forces operating across wildly different scales. This binding has consequences for the universe's long-term evolution. As expansion accelerates due to dark energy, gravitational islands will grow increasingly isolated. Galaxy clusters will drift beyond one another's reach, eventually leaving local structures as the only objects that remain visible to distant observers in far future epochs. Over trillions of years, stars will exhaust their fuel, galaxies will dim, and the universe will become a landscape defined more by gravitational relics than by luminous structure. Yet gravity's hold ensures that even in such distant eras, matter will not dissolve entirely into the background. Clusters will remain intact, stellar remnants will linger in quiet orbits, and black holes will continue to anchor regions of curved spacetime. Gravity's hold also shapes the cosmic web, drawing mass along filaments and into dense nodes. Without the contrast between expansion and gravity, the web would not exist in its present form. Filaments form because gravity amplifies slight density variations, pulling material into elongated structures even as expansion widens the space between them. Clusters form at filament intersections, where matter accumulates over billions of years. Void regions expand faster, draining material outward, enhancing the contrast between emptiness and structure. In observational cosmology, the imprint of gravity's hold appears through gravitational lensing, where massive objects bend the path of light from more distant sources. This bending allows astronomers to map the unseen mass of dark matter halos, tracing the outlines of gravitational structure. It also reveals how bound systems distort spacetime in ways that expansion cannot erase. Even as the universe widens, these local curvatures persist, anchoring matter against the cosmic tide. There is a quiet comfort to gravity's hold amid the vastness of cosmic expansion. It allows stars to form, planets to orbit, and galaxies to persist long enough for complexity to arise. In a universe dominated by widening distances, gravity provides the counterpoint, an enduring presence that shapes the environments where life might emerge. Its influence softens the relentlessness of expansion, offering continuity within an ever-growing cosmos. Yet even within these gravitational sanctuaries, subtle shifts lead us onward, for among the billions of galaxies shaped by this delicate balance, most move steadily away under expansion, except for the rare few that edge inward, defying the larger trend. These unusual cosmic neighbours form the next piece of the unfolding narrative, illuminating the limited but intriguing circumstances under which galaxies approach rather than recede. Rare approaches. Across the immense distances of the expanding universe, where nearly every galaxy drifts outward in quiet compliance with cosmic expansion, There exists a small collection of exceptions regions where gravitational attraction overwhelms expansion and galaxies move toward one another. These encounters, described collectively as rare approaches, stand out precisely because they defy the dominant outward trend. They reveal the intimate side of cosmic structure, showing how gravity can reverse the widening of space in specific circumstances and draw galaxies into eventual merger. The most familiar example lies close to home: the Andromeda Galaxy, our spiral neighbour situated roughly 2.5 million light-years away. Andromeda is moving toward the Milky Way at about 110 kilometers per second, a blue-shifted signal that betrays its incoming trajectory. This is a textbook demonstration of how gravitationally bound systems operate differently from the larger universe. Despite expansion acting across intergalactic space, the gravitational pull between the Milky Way and Andromeda exceeds any separating influence. Their mutual orbits tighten over time, and in roughly 4 billion years, they will merge into a single elliptical galaxy. This future union is not an accident. It is the natural conclusion of gravitational dynamics acting in a local region of high mass density. Beyond our local group, other rare approaches appear in galaxy clusters, where thousands of galaxies orbit within a shared gravitational envelope. In these dense environments, galaxies frequently interact, experience tidal distortions, and occasionally collide. The Virgo cluster, for example, contains hundreds of galaxies moving in complex gravitational dances, with many falling inward toward the cluster's core. Expansion plays no role inside such regions. The cluster is gravitationally bound, insulated from cosmic widening. Galaxy groups also exhibit their own rare approaches. Smaller systems, such as the Sculptor group or the M81 group, contain galaxies migrating toward one another as gravity redistributes mass over cosmic time. In these environments, interactions are common. Dwarf galaxies fall into larger hosts, hot gas streams form elongated bridges, and dark matter halos merge in the background. These processes shape galaxy evolution, triggering bursts of star formation or disrupting stellar orbits as galaxies draw near. Rare approaches also occur in interacting pairs observed far beyond the local universe. Telescopes reveal striking examples such as the Antennae galaxies, where two spirals are caught in a dramatic collision, their stars flung into tidal tails that arc across space. The Cartwheel Galaxy shows the result of a head-on encounter that generated concentric waves of star formation. Systems like these provide direct evidence that galaxy mergers are a common part of cosmic evolution, even if each individual approach is localized and rare relative to the universal trend of recession. These interactions are driven fundamentally by gravity's dominance over small regions of the cosmic web. In areas where matter density rises above the average, gravitational attraction increases correspondingly, allowing these regions to resist cosmic expansion. Dark matter plays a central role. Its halos provide the gravitational wells into which galaxies fall. Without dark matter, the number of rare approaches would diminish significantly, and many structures that now merge would instead drift apart. The distinction between approaching galaxies and receding ones highlights the delicate balance between expansion and gravitational binding. At distances of tens of millions of light-years, expansion typically dominates, causing galaxies to separate. But within a gravitationally bound region, such as a cluster or group, interactions become inevitable. The boundary between these two regimes is defined by the strength of gravity relative to expansion beyond that limit. Galaxies drift apart. Within it, they converge. Rare approaches also illuminate the future of gravitational structure. As universal expansion accelerates under dark energy's influence, fewer galaxies will remain close enough to experience mutual attraction. Over many billions of years, all but the most tightly bound systems will drift beyond one another's reach. Galaxy mergers within clusters will continue for some time, but eventually, even clusters will stand alone, surrounded by galaxies, forever lost beyond the cosmic horizon. In such a universe, rare approaches will become even rarer, leaving only local gravitational families as remnants of the interconnected cosmos that exists today. While these encounters are exceptional in an expanding universe, they are essential for understanding galaxy evolution. Mergers fuel the growth of massive galaxies, trigger periods of intense star formation, and redistribute angular momentum. Supermassive black holes at galactic centers may merge as well, releasing gravitational waves detectable across cosmic distances. These waves serve as yet another form of distant signal, marking the culmination of rare gravitational unions. Despite the universe's tendency towards separation, these intimate interactions remind us that gravity still draws matter together in remarkable ways. And from the quiet gravitational pull that binds galaxies into rare convergences, a broader narrative unfolds, one that guides us toward the shifting boundary between what remains bound and what escapes into the ever-widening cosmic expanse. Local motion. Deep within the quiet expanse of our galactic neighborhood, where gravity weaves subtle threads between scattered islands of stars, the concept known as local motion describes the movements that occur independently of universal expansion. While most galaxies drift apart under the widening fabric of space-time, the objects within smaller, gravitationally linked regions follow their own paths, orbital arcs, slow infalls, or gentle drifts shaped entirely by the mass around them. These motions do not contradict expansion. They exist alongside it, sheltered within environments where gravity outweighs the separating influence of the cosmos at large. Our own Milky Way provides the clearest demonstration of local motion. At the scale of the galaxy, stars orbit the galactic center in a vast, rotating disk. The Sun completes one revolution roughly every 230 million years, carving a path shaped not only by the visible stars and gas, but by the dominant presence of dark matter, whose gravitational influence sculpts the rotation curve. Local motion here is ancient and persistent. Each star follows a trajectory carved over billions of years, slightly perturbed by passing stellar neighbors or subtle density waves that spiral through the disk. At this level, the expansion of space is entirely irrelevant. The gravitational binding energy of the galaxy overwhelms the minuscule stretching of space-time that expansion would otherwise impose. The same logic extends outward to the local group, a gravitational family of over 50 galaxies that move in relation to one another, bound by a combined mass far greater than the individual galaxies it contains. Within this collection, the Milky Way, Andromeda, and Triangulum dominate their dark matter halos, overlapping enough to create a region where gravity nullifies expansion. The local group spans about 10 million light-years, modest on cosmic scales, and yet it represents a sanctuary in which expansion cannot pry galaxies apart. Instead, they drift, orbit, or fall toward one another in slow, deliberate motions, shaped by millions of years of interaction. The most famous example lies in Andromeda's motion toward the Milky Way. Observations show a blue shift in its starlight, revealing that it approaches at about 110 kilometers per second. Rather than being swept away by expansion, Andromeda is drawn inward by our galaxy's gravitational influence, just as we are drawn toward it. Their mutual trajectory points toward an eventual merger several billion years in the future, when their disks will interpenetrate, stars will be scattered into new orbits, and a massive elliptical galaxy will form. Local motion is thus not merely a footnote to cosmic expansion, but an active process shaping the long-term identities of galaxies themselves. Beyond the local group lies another layer of gravitational influence, the Virgo cluster. Our group moves toward this dense congregation of thousands of galaxies at several hundred kilometers per second. This motion arises from the collective gravitational well of the cluster, which spans tens of millions of light-years and outweighs the local group many times over. And even Virgo is part of something larger still. Superclusters such as Hydra Centaurus and the Laniakea supercluster, whose combined mass directs the flows of entire galaxy groups. Such movements, known as peculiar velocities, reveal the subtle interplay between gravity and expansion motions that deviate from the general trend, showing where gravity's hand still guides the dance. Local motion appears at smaller scales as well. Within globular clusters, tens of thousands of stars orbit in tightly packed spheres, some of the oldest structures in the Milky Way. Their motions are gentle yet precise, held together by an extraordinary concentration of mass. Planetary systems add another layer. Planets orbit stars with no influence from expansion, for the gravitational binding energy between a star and its planets exceeds any cosmic stretching by many orders of magnitude. Expansion simply cannot compete on such intimate scales. All of these motions demonstrate a fundamental truth. The universe is not governed by a single, uniform behavior. Instead, it is partitioned into regimes where different forces dominate. Expansion reigns on the largest scales, driving galaxies apart across distances of hundreds of millions of light-years. Gravity dominates in smaller regions, galaxies, groups, clusters, systems, ensuring that motion remains local and structured. These two regimes coexist, never conflicting, each acting where its influence is strongest. Local motion also enriches our understanding of cosmic history. The structures we observe today formed through the gradual collapse of matter into gravitational wells. Galaxies migrated along filaments of the cosmic web, funneling toward denser regions. Their motions reveal past interactions, past mergers, and past gravitational influences. By mapping local motion across the sky, astronomers can reconstruct the distribution of dark matter, identify unseen mass concentrations, and trace the hidden scaffolding of the universe. These interwoven motions guide galaxies across local regions of the cosmic web. A deeper question naturally arises not about how matter moves today, but about how it all began. The pathways of galaxies, the formation of stars, and the very structure of space itself lead inevitably back to a far earlier epoch, when everything matter, radiation, and space-time was compressed into a state so dense and hot that the familiar universe could not yet exist. It is toward this earliest chapter, preserved in cosmic radiation and elemental abundances, that the next story turns. Big Bang Story. In the distant depths of cosmic history, where time narrows toward a beginning too hot and bright for stars or atoms to exist, the Big Bang Story describes the origin and early evolution of the universe from its first measurable fractions of a second. Rather than an explosion into empty space, the Big Bang refers to the expansion of space-time itself, an unfolding of the universe from an initial state of extraordinary density and temperature. Everything observable today traces its origins to this early phase. Every particle, every force, every structure, and every law operating within the cosmos. Our scientific account begins at an epoch so brief it challenges intuition. At around 10 to the power of -36 seconds, the universe underwent cosmic inflation, a phenomenon first proposed by Alan Guth in 1980. Inflation describes a phase of exponential expansion driven by high-energy fields permeating space. During this impossibly brief interval, the universe grew from subatomic scales to astronomical dimensions. This rapid stretching smoothed out any irregularities and flattened the curvature of space-time, producing the nearly uniform cosmos we observe today. Quantum fluctuations, minuscule variations in energy, were stretched across cosmic scales, becoming the seeds from which galaxies, clusters, and the cosmic web eventually formed. When inflation ended, the universe continued to expand, but at a slower, steady rate. Temperatures remained extreme, far hotter than the cores of stars and particles formed and annihilated rapidly. As the universe cooled to around 1 trillion degrees, the fundamental forces separated into their familiar forms. At this stage, matter began to stabilize. Quarks combined into protons and neutrons, and 3 minutes after the beginning, Big Bang nucleosynthesis commenced. During this process, the first nuclei formed: hydrogen in abundance, helium at about 25%, and traces of lithium. These precise proportions serve today as one of the strongest confirmations of the Big Bang model. For hundreds of thousands of years, the universe remained a glowing plasma of electrons, protons, and photons. Light could not travel freely. It scattered off charged particles in every direction. But as expansion continued, the universe cooled to about 3000 Kelvin, cool enough for electrons to combine with nuclei and form neutral atoms. This era, known as recombination, transformed the cosmos. Photons, no longer trapped by scattering, streamed outward across space. Those photons still fill the universe today as the cosmic microwave background, CMB, discovered in 1965 by Arno Penzias and Robert Wilson. The CMB is a nearly uniform bath of microwave radiation, but sensitive instruments reveal slight temperature variations, tiny imprints of the early density fluctuations shaped during inflation. Over the next hundreds of millions of years, the universe expanded and cooled further. With atoms now abundant, gravitational forces slowly amplified the initial fluctuations into denser regions where gas accumulated. Roughly 200 million years after the Big Bang, the first stars ignited massive, brilliant, and short-lived. Their ultraviolet radiation reionized the surrounding gas, ending the cosmic dark ages and illuminating the early universe. When these stars died as powerful supernovae, they seeded space with heavier elements, enabling the later formation of planets, complex chemistry, and eventually life. Galaxies began assembling during this period, drawn together under the influence of dark matter halos. Over billions of years, mergers shaped their morphology: spirals, ellipticals, irregulars. The cosmic web formed through gravitational attraction, guiding matter into filaments and clusters that remain visible today. All of this, the evolution of stars, the structure of galaxies, the spread of chemical elements, emerged from conditions set in the earliest seconds of cosmic time. Modern cosmology confirms the Big Bang story through multiple independent observations. The expansion of the universe, discovered by Edwin Hubble in 1929, matches the predictions of the model. The abundance of light elements corresponds precisely to nucleosynthesis calculations. The cosmic microwave background offers a snapshot of the universe just 380,000 years after the beginning, revealing its curvature, age, and composition. These lines of evidence converge with extraordinary consistency, forming one of the most successful scientific models ever constructed. The Big Bang story does not describe what existed before, nor does it require that time itself originated at a single point. It describes the evolution of the universe from the earliest moment we can meaningfully discuss using physics. What came earlier remains an open frontier, one that theories of quantum gravity and advanced cosmological models continue to explore. But within the measurable history of the cosmos, the Big Bang framework provides a coherent, richly supported account of how the universe expanded, cooled, and organized itself into the structures we observe today. These early conditions echo across cosmic time, from the faint glow of the microwave background to the arrangement of galaxies stretching across billions of light years. They guide us toward the next unfolding thread, how these initial forces continue to shape the present universe, establishing the foundations upon which all cosmic motion and structure now rest. Ancient echoes. Across the quiet darkness that surrounds every galaxy and every star, there lingers a faint, ancient whisper, an imprint from a time when the universe was young and incandescent. These ancient echoes appear today as the cosmic microwave background, a diffuse bath of radiation stretching across the entire sky, marking the oldest light we can observe. In the first sentence of this segment, ancient echoes refers to the remnant photons that escaped when the early universe transitioned from an opaque plasma into a transparent expanse, preserving a near-perfect record of conditions only 380,000 years after the Big Bang. They are not echoes in sound, but echoes in light, carried across billions of years to reach us. This radiation was first detected in 1965 by Arno Penzias and Robert Wilson, who attempted to eliminate a faint hiss from their radio antenna. It persisted regardless of direction, season, or calibration. Only later did they realize the signal matched the predicted temperature of the universe's primordial glow. These ancient echoes have since become one of the cornerstones of cosmology. They offer a snapshot of the universe at a far earlier epoch than any telescope observing stars or galaxies could ever reveal. In that early era, free electrons scattered photons relentlessly, preventing light from traveling freely. But once the universe expanded and cooled enough for electrons to combine with nuclei forming the first neutral atoms, light was suddenly liberated. Those freed photons now arrive at Earth from all directions, stretched into microwave wavelengths by billions of years of cosmic expansion. Modern instruments have studied these echoes in exquisite detail. NASA's COBE satellite first measured their uniformity, revealing a temperature of roughly 2.725 Kelvin, only slightly above absolute zero. The signatures showed extraordinary smoothness, differing only by tens of millionths of a degree. Yet within these subtleties lay crucial information. Later missions, including the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, unveiled precise maps of temperature fluctuations across the sky. These fluctuations represent tiny variations in the density of the early universe regions, where matter was slightly more or less concentrated. Over time, gravity amplified these variations, drawing matter into the cosmic structures we observe today: galaxies, galaxy clusters, and the vast filaments of the cosmic web. The ancient echoes also reveal the geometry of the universe. The patterns in their temperature distribution indicate that space is remarkably flat on large scales. This observation aligns with predictions from cosmic inflation, which stretched space-time to extraordinary extents in the universe's earliest moments. Through these echoes, we can measure the universe's age, the strength of its primordial fluctuations, and the proportion of dark matter and dark energy that shapes its expansion. No other source offers such a direct window into the earliest chapters of cosmic history. The echoes contain more than temperature data. Polarization mode's tiny alignments in the radiation's electric fields offer clues about the interactions between matter and photons in those early epochs. These signatures reveal how sound waves moved through the primordial plasma, creating pressure patterns that later influence the distribution of galaxies. Some patterns arise from the gravitational lensing of background light as it passes through intervening matter, providing a method of mapping dark matter across the cosmos. Even subtle effects such as the Sachs-Wolf imprint, small shifts in photon energy caused by traveling through gravitational potentials, preserve information about the universe's earliest large-scale structures. These ancient echoes are not static relics. They still influence modern cosmology. Their precise measurements allow astronomers to constrain the Hubble constant of the current rate of expansion of the universe. Curiously, values derived from the echoes differ slightly from those obtained by observing nearby galaxies using supernovae and Cepheid variables. This tension, known as the Hubble discrepancy, hints at either new physics or deeper complexities in our cosmic understanding. In either case, the echoes remain a guide, illuminating paths that future theories may take. Their significance stretches beyond scientific measurement. These ancient echoes remind us that the universe carries memory that light can bear witness across time. They reveal a cosmos that began in smoothness but contained just enough irregularity to grow into complexity. The earliest whispers have become the grand structures of galaxies, stars, and life. These echoes, faint though they are, remind us that every atom, every orbit, and every movement in the universe arises from conditions imprinted at its beginning. And as these primordial signatures continue their long journey across space, they lead us naturally to consider how the universe has moved since that earliest light was released, how galaxies, clusters, and even our own Milky Way drift through a cosmos shaped by expansion and gravity alike, weaving paths across a dynamic and restless universe, our moving cosmos. Across the immense sweep of the night sky, galaxies drift as though carried by unseen currents, each one tracing a unique path through an ever-widening universe. This segment, titled Our Moving Cosmos, refers to the combined motions that shape the universe on both local and cosmic scales, the expansion that stretches space itself, the gravitational influences that guide galaxies into clusters and superclusters, and the intricate movements that reveal the structure of everything around us. In its first sentence, Our Moving Cosmos describes the profound truth that the universe is never still. The largest component of this motion is the expansion of space. Ever since Edwin Hubble first observed the redshifts of distant galaxies in 1929, astronomers have known that galaxies beyond the local group are receding from us. This recession is not ordinary motion through space, but motion caused by the stretching of space itself. The farther a galaxy lies, the faster it appears to move away, a relationship known as the Hubble-Lemaitre law. Observations using supernovae, baryon acoustic oscillations, and the CMB confirm that the expansion is not slowing, it is accelerating, driven by dark energy, a mysterious component that makes up nearly 70% of the universe. Yet cosmic expansion tells only part of the story. Within gravitationally bound systems, galaxies, clusters, and groups gravity counters expansion. Stars orbit galactic centers. Galaxies orbit within clusters. Clusters drift within supercluster filaments. These relationships form a layered structure of motion, each scale governed by different forces. The Milky Way, for instance, spins at around 220 kilometers per second at the Sun's location. The Sun itself spirals around the galactic center, carrying planets, moons, and comets in a complex orbital ballet that has unfolded for billions of years. On larger scales, our galaxy participates in broader flows. The Milky Way and Andromeda move toward one another, bound by gravity. Together they fall toward the Virgo cluster, which sits at the center of the Virgo supercluster, a sprawling assembly of thousands of galaxies. Beyond this local landscape, an even greater motion asserts itself. Our entire region flows toward a gravitational anomaly known as the Great Attractor, a dense concentration of galaxies obscured from direct view by the plane of the Milky Way. Farther still lies the Shapley supercluster, whose immense mass influences motions across hundreds of millions of light-years. These layered movements form a cosmic hierarchy, each revealing deeper structures in the universe's distribution of matter. Our moving cosmos is also visible in the cosmic microwave background. The CMB contains a dipole, anisotropy, a slight temperature difference across the sky, caused by our movement relative to this ancient radiation. Measurements show that the Milky Way travels at roughly 630 kilometers per second in a specific direction. Its motion shaped by combined gravitational influences. These motions are not random. They reveal the underlying distribution of dark matter, which forms the skeleton of cosmic structure. Where dark matter concentrations are high, galaxies fall inward. Where it is sparse, they drift outward into expanding voids. Observations of these flows allow astronomers to map dark matter indirectly. Peculiar velocities, deviations from the expected motion due solely to expansion, serve as indicators of hidden mass concentrations. Every movement becomes a clue, every drift a signpost pointing toward deeper gravitational landscapes. The interplay between expansion and gravity also shapes the cosmic web. Filaments act as conduits for matter, guiding galaxies toward nodes where massive clusters reside. Voids expand faster than average, pushing matter into surrounding filaments. Meanwhile, dark energy stretches the fabric of space on the largest scales, pulling distant regions away from one another so rapidly that, in time, only the closest gravitational families will remain visible. These motions influence the evolution of galaxies themselves. Collisions trigger bursts of star formation. Mergers reshape structures. Tidal interactions distort spiral arms. Even the quiet drifting of galaxies through intergalactic gas leaves trails detectable through X-ray emissions. Motion is not merely a passive outcome, but an active sculptor of cosmic history. Our moving cosmos serves as a reminder that the universe is not static, nor has it been at any point. Everything drifts, everything responds to gravity, and everything unfolds within the larger context of expansion. The paths of galaxies tell us where matter lies. The speeds of clusters reveal hidden masses. The cosmic background tells us how the universe itself moves beneath our feet. And as these motions combine across scales, from the sweeping arcs of galaxies to the subtle pulls of superclusters, they lead us toward a deeper recognition of the forces that bind the cosmos and guide its evolution, opening the way to the next layer of understanding in this unfolding cosmic journey.